step forward, which is not in the theory and conceptual part, but on the practical part. So what is about? You know, it's about what is indicated here. So we need to see what is a moving average process, what is an autoregressive process, and what is how can we compute the autocorrelation. Now, so you know, and then we do it in numerical. Okay. Now if we have a moving average, okay, so assume that we have a system, okay, which is excited by Wn. Wn is a wide sequence. When I say wide sequence, means that the autocorrelation of W, k, okay, is equal to a certain scalar function, which is the power, multiplied by delta k. Okay, so it's it's a sigma square on delta k, so k equals 0 and all the other is 0. Okay, so now this wide process is exciting a system which has the z transform of the impulse response is bz. Okay, so bz is limited. Okay? So it's a polynomial. So let's say that the polynomial is order nb, which means it's a polynomial order nb. So which means that the sequence of sample is nb plus 1. Okay? Now, so my goal is to get the output is xn. So my goal is how to compute rxxk. Okay? This is a typical, let me say, since you like desperately, you want to have a prototype of the exam, right? So you want to find something that, what is this? It goes and this, I'm using that formula, right? Okay, so I'm moving toward you, so, you easily frame everything into a specific concept, huh? So now, how to compute that? Now, in order to compute this one, okay, I need to notice that the sequence, that one is a sequence. Okay, so the autocorrelation is a sequence, and that sequence is computed by, by taking the autocorrelation of the input, which is a delta, with the autocorrelation of the filter. Okay, which says a certain function. Okay, so if I need to compute this one, that one is Rxxk is equal to Rbbk convolve with Rwwk. Okay? In Z transform, this is equal to Rxxz equal to Rbbz multiplied by Rwwz. Okay. Now, how is the Z transform of the a white noise? So that means that I need to compute the Z transform for that. So it's a delta. Okay. So it's simply, the Z transform Rwwz, okay, is equal to sigma squared W. That's it. Okay. So then, I take this one. Okay. I plug into there, and it comes out that the Rxxz, which is the Z transform of the autocorrelation sequence, is equal to Rbbz multiplied by sigma squared W. As simple as that. What is the RBB? RBB is simply taking the sequence B and B, Z, and then multiplying, which is convolve. How to compute the autocorrelation of a filter. Compute the autocorrelation of a filter is to convolve the filter with itself, swapping the axis. Okay, so it is to convolve. So convolution becomes a multiplication in Z transform, is So it's a convolution with the sequence swapped in time. And if it is complex, I need to make the complex conjugate of every coefficient. Okay? So, by the way, let me make an additional comment. Okay, comment. Comment is the following. So, B and B Z as n B zeros. Okay, then R B B Z contains how many zeros? Now the sequence is NB plus 1. I convolve with another NB plus 1, which makes 2NB plus 2 minus 1. Okay, so the sequence length is, let me write it, because you know, I see you staring at me like if I'm saying, you know, something very magic. You prefer to write here because it remains, huh? For me, it's more convenient to stand up and okay. So, what is the autocorrelation? So R, what was B? R, B, B, no, it's in red. R, B, B, K. Okay, that one is the autocorrelation of the impulse response of the filter. Okay, now this one is Bn, which is the impulse response, convolved with the B star minus n, which means this minus n means flipping the axis. Okay. So now in Z transform, by the way, if this one is NB plus 1, that one is NB as well. Here. NB plus 1 as well. Okay? So the length, the total support of the convolution, so the length, is equal to NB plus 1 plus NB plus 1 minus 1. Is the sum of the first, sum of the second minus 1. Okay? So it is equal to 2 times NB plus 1. Okay? Now, since the autocorrelation is symmetric, okay, so we expect that the autocorrelation, you know, is at a leg 0, so at a delay 0. This is k-axis. So I have a set of coefficients that are, I don't know, symmetric, okay? Oh, maybe 3, 1, 3. Okay. So the length is NB, the other is minus NB. So the total makes 2 times NB plus 1. Because plus 1 is the 0, okay? So the shape, the polynomial, you know, is symmetric, okay? Recall that, you know, RBBK is equal to RBB star minus K. If real, that means that RBBK is equal to RBB minus K. Okay? So it's even symmetric. Okay? So, you know, these are part of something that telecom must know. Absolutely. There is no question on that. If the telecom doesn't know, you're better to change the degree. I'm serious, okay? So telecom must know. So if you guys don't know, you're better to reconsider, I would say, your career. Because, I mean, this is like, I don't know, 1 plus 1 makes 2, you see? Okay, 2 plus 2 makes 4. Okay, and if you have a fantasy, it makes 5. But you know, I have heard that, I mean, 2 plus 2 makes 5 because I want to fight against the people that are building the calculator, the computers. Okay, so anyway, so that's a political matter. So anyway, so this is you know, conventional. Okay, now let's look at in the z-transform. So in the z-transform, that means that when I take the first one, so when I make the z-transform for Bn, okay, this is Bz, which has a length nb. So when I make the z-transform of B star minus n, okay, so I swap the axis, change the axis, okay? So what does it mean, change the axis? Okay, so B star means that, you know, I make the complex conjugate of the sequence. And then, you know, 1 over z means time reversing. Okay? Now, convolution means a product, and then, you know, here it comes. Is it clear? Please, I write it here, okay, because when I was writing there, but then I said, what about if perhaps someone has not a clear idea of that? So, you know, I wrote it here. Okay, so let me go here. So this is, you know, this is the result. So what I need to do, I need to calculate. So the way to do it is make the z-transform of the sequence, and then, you know, after doing the z-transform, compute the z-transform time. So in this way, z-transform of the sequence multiplied by the z-transform of 1 over z of the sequence, complex conjugate if they are complex. And then we get the z-transform of the autocorrelation. So the autocorrelation is computed in z-transform. Okay? Number 1. Second preliminary. Okay? The second preliminary. How to compute the autoregressive? Now for the autoregressive, the story is different. Okay? Is different. By autoregressive, I'm using the formula here. So let me copy and paste. Okay, so I use this setting. Now, for autoregressive, use the definitions. And by the way, for autoregressive, use the definition in a wise way. Okay, which means, you know, I mean, if you are in trouble, use the definition. Always, when you are in trouble, use the definition. And you know, no matter how long it takes, you will reach the conclusion. So the end. Okay. So the way to compute the autocorrelation in this case is by using the Euler-Walker equations. Now, I am going to derive now the Euler-Walker equation. So how is so if it is autoregressive, one second. So if it is autoregressive, that means that B does not exist. Okay? So for autoregressive, you calculate, you know, the autocorrelation by assuming that the filter is that one, okay, where you have only poles. Okay, our system. Now, let's use the Euler-Walker. How to derive the Euler-Walker? So this is the first time we derive the Euler-Walker. Okay, so it's much easier than you can imagine. And since we will see Euler-Walker equation in 3 cases, but for the intermediate exam we will use only once. So I mean, this is in these cases to compute the forward problem, which is by the filter calculate the autocorrelation. So you're better to get practice with the Euler-Walker. Now let's make it. So Euler-Walker is made in this way. How to calculate RXS? Okay. So Rxxk by definition, okay? So I'm like a stupid, you know. I'm using definition. I never make a mistake, okay? Let's make it to simplify. Okay, X and A, L are real. Okay, just to simplify. Okay, coefficient and so are real. So everything is real. So we don't need to take the headache for computing with the complex ones. If complex, okay, verify yourself for complex. Okay, so you make it by yourself. This is a homework exercise. Now I make for a real. So I use the definition. So the definition is, you know, is expectation of it is xn plus k. Okay, and I need to take the expectation. Okay, fine. Now, you know, when I need to take the expectation, I need to remember what is xn. So if I look at xn, and this is the finite difference equation, so this is equal to xn equal to minus, there is the recursive part, so it is for L equal 1 to NA, it is AL, and then it is X and minus L, and then there is the excitation, okay, which is W plus WN, okay. So this is the finite difference equation corresponding to this linear time invariant filter. Now, so what I do is the following, you know, I plug in I replace this term with a definition. So with the definition of the recursive part. So you know, in order to replace, I need to write xn plus k. So what is n xn plus k? So just copy the photocopy. It's a sum L equal 1 to NA, and it is AL, and then it's x n plus k minus L plus W n plus k. I simply, you know, substitute it. Okay. So what I do is I take this and I move it. That's all I do. Okay. Now I need a new page, so I just copy this and move it in a new page, so that again you don't lose anything. Here it is. Okay. So when I move and when I plug into that, I have Rxk equal to expectation with respect to xn. Then you know I'm just multiplying. So that is, you know, it's minus that one. So I mean they make it this way. I want to say space. So it is all that. Okay. Now this is equal to minus sum over L equal 1 to NA of what? Of AL expectation of xn xn plus k minus L plus the expectation of where is it? Here, xn W n plus k. Okay. Now, but you know, if I look at this one, this is Rxx evaluated in k minus L. Okay. So, you know, I simply copy that, and I plug into that, And then it comes out that this is minus sum of L equal 1 to A L Rxx of K minus L. Then I have this, the other, plus plus that. Look at this. This is the noise. Noise is white, right? So, so basically what I have is Xn. So I should now take this Xn, use a different color. I should plug that one into there. Now, let's look together. If I take that one and move into there, here there is W n plus K. Remember, W is white. So this one is only correlated with itself. So that means that when I plug that one into there, there is n minus K, blah, 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 and then there is Wn. So the only term that matches with this is Wn. Okay? So the only terms left is the expectation of Wn, and then I have Wn plus K. But this one is the autocorrelation of the noise, or the excitation, and the excitation is a white process. So since this one is a white process, that one, is equal to sigma squared W multiplied by delta K. So we have the celebrated Euler-Walker equation, which is the equation that we are going to use today, okay? Which is Rxxk plus, so I take the right and move on the left, okay? It is plus sum L equal 1 to NA AL Rxx K minus L equal to sigma squared W delta K. It's this one. Okay. So this is the Euler-Walker equation that we will indicate shortly as Euler-Walker. Okay. This is the Euler-Walker equation for autoregressive process of order NA. Now, so let's make it, one simple case. Now we are entering into the exercise. For instance, it's not here in these four, but I remember that I don't know when, but the past year, I gave an exercise which was to prove that what is the autocorrelation in autoregressive order 1 process. So AR1, okay? So let me, make it together with you. So, is it clear up to here? So, is it clear? All the steps I made? In case you don't have, by the way, I think a Euler-Walker equation is one of those that the students last year wanted to put into the back of the exam, because into any exam, into any written exam, you have the possibility to include, I think it is 10 equations. I don't know. Is it 10? Okay. So you have 10 equations. So you all together agree on 10 equations that you can put on the back of the page. So every time you have the exam, the text, okay? So every time you have a text, on the back of the text, there is this equation, okay? So, and the Euler-Walker are one of those, and you are right, because these are important, okay? But in case you are desperate, wherever, it's not complicated to write, even the Euler-Walker. What you should not do, let me tell you, the mistake. What you should not do when you need to prove the Euler-Walker, you should not replace any of the equation with a recursive formula. Because after a while you have two sum and you don't understand anything. Okay? So be smart on the right in case you need to do it. Now let me make the exercise. So evaluate or prove, I don't remember the word I used in the example. So, evaluate Rxxk for autoregressive order 1 system or process. So what does it mean? So it means that we have our system where we have the white process here, which is excited by a power. Okay, so it's white, and I underline here the power. This system is filtered by a filter where I have a rho z to the minus 1. So it's a one pole, okay? My goal is to get xn of the output xn. What is the output order? And rho is smaller than 1, okay? So the filter, since rho is smaller than 1, that means that the pole is in z smaller than 1. So it is in the unit circle, okay? It's internal to that. So since that the system is causal, okay? When I say causal, it means stable, because we are engineers, so we don't speculate on the system. We only consider system that we can do it, okay? System that mathematically can do it is not of our interest, because we can talk on that, but this is not the place where we talk about it. Okay? You are in engineering school, so this is what you need to get used to. So anyway, so this is the setting of the problem. Now, how to solve it? Let me say, start solving here. Okay, how to solve it? Now, in order to solve it, I need to use the Euler-Walker equation, which is, the equation is Rxxk, then it is the coefficient, the first coefficient, which is minus rho Rxx1 k minus 1, okay, is equal to sigma squared w multiplied by delta k. How I make it now? So my unknown is Rxx. So let me underline here the unknown. Okay, these are my unknown. So since I have two unknowns, I need to write two equations, right? And so I can start writing the equation where I have Rxx0 minus rho Rxx minus 1 is equal to sigma squared w. So I write the equation for k equals 0. Then I can write the equation for k equal 1. Now the equation for k equal 1 is Rxx1 minus rho Rxx0 is equal 0. Okay? So I have, I have two systems, two equations in two unknown. Now, recall that Rxx is symmetric. So since it is symmetric, Rxx minus 1 is equal to Rxx1. Okay? So, it is convenient to write this as a system and as a matrix. So I started writing as a matrix. So, I write my unknown and my known term. So let's fill it. Here I have Rx at 0. Here I have Rx x 1. Okay. Now, let's take the first equation. So I have 1, and then I have minus rho. AD is equal to sigma squared W. The second equation, the unknown term is 0, then it is minus rho, and then it is 1. Okay? So, so I can get Rxx0 and Rxx1. Okay? So solving for Rxx0 and 1. Okay, I get by solving, I get this one. I get that Rxx0 is equal to 1 divided by 1 minus the determinant, which is rho squared. When I get Rxx1 is equal to 1, so it is rho divided by 1 minus rho squared. Now, I continue to apply the formula. So the formula says, I want to get Rxx2. So Rxx2 is equal to rho Rxx1. So, which is equal to rho square divided by 1 minus rho square. So I make it again. I make Rxx3 is equal to rho Rxx2, which is equal to rho cubic divided by 1 minus rho square. So I can generalize, which is Rxx k is equal to rho to the power of k divided by 1 minus rho squared. And now, this formula should be symmetric. If k is positive, it's this one, but it should be the same for k negative. Okay? So, then I put the absolute value on k, and this comes from symmetry. Okay? Clear? Okay, so if the question is, oh, I forgot sigma square. My fault. So sigma square is a scaling factor. Okay. So if my question is, what is the power of the random process output of the filter which has one pole? And the answer is that you need to solve by the Euler-Walter. Find all the coefficients, including 0, and then by solving the system, you get the power. I say it again. To get the power of xn, okay, in autoregressive order NA, arbitrary, okay, so the general rule, to get the power xn, xna, okay, you should solve for Euler-Walter for all terms included Rxx0, which is giving the power. Okay? So to get the power, which means Rxx0, so if I want the power, You cannot say the power is this. You need to solve it. Not question that. This is the most common mistake. The most common mistake is when they ask you what is the power of autoregressive, I don't know. I cannot count how many desperate tentatives you made to solve it. Okay? So remember that. You need to solve a Euler Walker. There is no other way. If you solve it another way, you are rediscovering the Euler Walker. Okay? So last year, for the first time, I found a student that you wrote one page to solve a problem that was to be solved in 3 lines. Okay, but essentially, at the end of the story, he made the right results. But he rediscovered. He was a man, so he's he rediscovered the Euler Walker by himself. So I mean, I mean, one side, I was tempted to penalize him because he said, okay, you should have applied. But on the other sense, I am the one that I always say, if you don't know what to do, use the definition. So he used the definition, and at the end, he made no mistake. Really, he made no mistake. Numerically, it was correct. It was numerically correct. It was. So I said, okay, fine. So now let's make and by the way, do recall it. This is this autoregressive order 1. If I go back to last, when was it? A few days ago? No, yesterday. Yesterday. It seems. Where is it? Here. Yeah. You see, the exponentially correlated random process. Okay. Look at that. It's rho to the power of. So sigma square rho to the power of. Okay? So this is the exponentially correlated process. Okay? So what we just derived is the exponentially correlated process. So let me add just a note. So when you study, you try to put together all the pieces. Okay? Okay, so you can put together. Now let's make the numerical part. Here now, I go to the numerical. Okay, now this is taken from the intermediate exam of 2016, so a couple of years ago. It was done in 23 November because at that time we started in later. And the course was lasting till the end of January. Okay, so we anticipated that. Now let's look at that. So let's read. By the way, when you, the difference between life and the exams, and the difference between your colleague that passed the written exam very easily, is that reading the exam. So you need to read the text. You need to understand that the one that is writing the text is guiding you to solve it, which is different from real life. In real life, you have no one that is guiding you. Okay? So homework and the written exam is written such as to guide you. You know what guide means? Okay? To move you across the problem. So now let's read it together. Let alpha and beta normal, so these are 2 normal processes, so Gaussians, with 0 mean and the power is 1. These are 2 statistically independent wide random processes. Okay? So alpha and beta, they have nothing to do. Okay? Since they are Gaussian, I could have written they are uncorrelated, right? Because any random process that is Gaussian, if it is uncorrelated, it is independent. Okay? Because of the general property for exponentially distributed random variable. So there are now some random processes that are generated by filtering alpha and beta. So I have an alpha and beta, and then I generate a very strange, different kind of process. Now, how these are generated? So x1, the output of 1, is equal to alpha n minus 1 half alpha n minus 1 plus alpha n plus 1. So I'm taking only alpha. Okay? So that means that I'm taking only the input. Now if you don't see it, you might get practice that you can calculate by the z-transform. So if you are in trouble, you can apply the z-transform directly to the problem at hand. x2 is equal to 1 half x2 n minus 1 plus beta. Then I have x3 is equal to x2 minus 1 half x2 n minus 1 plus alpha. Okay? So these are, 3 different combinations. Now, let me sketch it. So let's start with the first. So what is the first? By the way, let me continue to read the text. Okay, so given that, characterize the process x1 if it is autoregressive moving average ARMA and evaluate its correlation sequence x1, okay, by using the definition or whatever. Do as you prefer. B is to evaluate the property of x2. C is to evaluate the property of x3. Okay. Now, and then D, consider the process by x1 plus x2 minus 3, blah, blah, blah. Okay. The number 3, the last one, which is usually the most difficult, is left at the end. Let's start it. Okay, so let's start with x1. So what is x1? X1 means that I have alpha n, which is filtered by a specific filter. Okay. Now, how is this filtered? If I make it a z-transform, so I calculate the z-transform of x1 and equal to the z-transform of the right. Okay. Now, if I calculate the z-transform of the right, it comes out that it is 1 minus 1 half z to the minus 1 plus z. Everything to the z-transform of alpha, and we call A. Okay. So now, this is x1z is equal to that one. So x1 is a moving average because it is obtained by AZ, and this AZ is a wide process. Okay, so when I filter a wide process by a filter with all the zeros, I get the moving average. What is the order of this moving average? What order? One, 2, 3. How much is that? How many say 1? Nobody. How many say 2? How many say 3? How many say I don't know? Now I tell you a trick in case. Okay. Now, if you're in trouble, make all the power to z to the minus 1. So if I make to the power to the z to the minus 1, that means that I can group, I can collect z on one side. Then that one is z, so it is 1. Then it is plus z to the minus 1 minus 1 half z to the minus 2. So this one has 2 roots. It has 2 zeros. Okay? Because the zeros are z, is given by the z to the minus 2 because it's the power of the polynomial. Okay, so the sequence has a length 2. Okay. Now let me make another question to you, because sometimes it comes. Suppose that I want to calculate the autocorrelation of the sequence x1 to the length of n minus 1. What is the autocorrelation? Okay, when I delay the sequence. What is the autocorrelation? Assume that I give you the autocorrelation of Rx1, x1, k is known. What is the autocorrelation when I delay by one sample? I mean, this should be quick. What is that? Is it Rx1 S1 k minus 1? Because I delayed the sequence by 1. Rx1 and x1 k minus 1. Because I delayed the sequence by one sample. This is another common mistake. This is a common mistake of the exam of the intermediate test. So I'm telling you, these are a mistake. Is it this one? Why not? Come on, you make this mistake. I mean, I'm sure that at least 5 or 6 of you will make this mistake. If I had the delay by one sample, you will, delay by one sample of the autocorrelation. Now, if you delay the autocorrelation by one sample, it makes no sense. Now, if I have a process, and the process is stationary, remember, it doesn't change anything if you delay one sample, if you anticipate one sample. So any delay is irrelevant in the computation of the autocorrelation properties. Please, write this big, because I want to avoid to see 5 or 6 of you writing me this stupid stuff. Please write, this is stupid. Don't write, this is stupid. Okay? It's a nonsense. It's a nonsense because I write here. Okay. Better, no? Now when I make the exercise, it comes to my mind some of those mistakes that you make it, and then numerically, it's not. Sometimes you can calculate everything if the problem is framed in the correct way. If just a change one delay, it's a disaster. So if I have a certain sequence xn, and I know the autocorrelation here, okay, if I take this sequence and I delay z to the minus 1, and this is yn, okay, so ryk is equal to rxxk because of the stationarity. Okay? A big mistake would be to say that ryk is equal to rxxk minus 1. Is a big mistake. Okay? If it is not clear to you why, please look at what I wrote, meditate yourself, reflect a little bit, sit, relax, look, reflect, blah blah, and then get convinced. So we are here, okay, so I added them. So that one, you know, is a filter. So this one is a moving average. So that one is BZ. So this BZ is obtained by this polynomial. Okay. Now, how to calculate the autocorrelation? So if I need to calculate the autocorrelation, I do by the z-transform. So the z-transform that I'm doing is this way. So I need to take Rx1, x1z, okay, since that one is a moving average order 2, then Rs1, x1z is equal to sigma square alpha multiplied by bz multiplied by b star 1 over z, which is, I can use the original sequence, so I don't need to anticipate the relay. So if that one is 1 minus 1 half z to the minus 1 plus z multiplied by 1 minus 1 half z plus z to the minus 1. Then I simply multiply. Okay, so I simply multiply, then I make a 1 minus minus is plus 1/4 minus plus is plus 1. Okay, so here I added all this. So this multiplied by that, this multiplied by that, and that one is multiplied by that. Okay, this goes in green. Plus. Then I make everything related to z plus z to the minus 1, which is equal to, then let me change the color, so I use this pinky one. So I have 1 times 1/2, and then I have first 1/2 plus 1. Then I have this one is that. Then I have the second one with minus 1/2. With that, no, and then it is 1 to z to the minus 1. So if I made no mistake, it should be 1. Then the third one, plus, no, I use already this color, and I make the red, plus, then with the red I have z to the minus 1 and minus 1, which is equal to minus 1/2 z to the minus 2. Okay, is z to the minus 2 plus z to the square. Okay, so it should be this one, unless I did some mistake. So the sequence is, this one is 2 plus 1/4, so it is 2.25, or, you know, it is 2 1/4 4 8 9 4, okay, plus 1 minus 1/2, so it is z plus z to the minus 1 minus 1/2 z to the minus 2 plus z to the square. So that is the autocorrelation. The autocorrelation is already given that way. Okay. So now I copy. So the autocorrelation Rx1 x1k Once you got this autocorrection, you can write as a delta. So that one is 9/4 delta k plus 1. So it is delta k minus 1 plus delta k plus 1. And then minus 1 half. So minus 1 half delta k minus 2 minus 1 half delta k plus 2. Okay. That's a sequence. Or an alternative way. Okay, so this is, you know, the output one, the output of the first. So we can represent it graphically. So I put 0 here. I have a sample 1. And I have a sample 2. So it is 9/4 which is 2.20. Then in 1 it is 1. Then in 2 it is minus 1. Now notice, if I need to represent as a plot, as a graphical illustration, okay, please, I need to see what is the axis, okay, you know, where is the 0, where is the 1, where is the 2, where is minus 1, where is the minus 2, and then is the value. Okay. So if you need to represent graphically, you need to indicate everything. You can choose whatever as the output. And this one, you know, is closing the first question. The second. Okay. Now the second is as a filter, and the filter is autoregressive. I still copy. Actually, since you have everything in Dropbox, you don't need to copy. So my goal is not to copy it. Okay. Now the second says, now please calculate. This one is x1. The second is, I have x. Look at that. It is x2 is equal to 1/2 x2 and minus 1. So this one is taking the past and used to calculate the present. Plus beta. Beta now is the input. So it's the excitation of the system. Okay. So now if I need to describe this system, if I make a z-transform, so let me make a z-transform on the fly now. Okay, which means I make it directly in the equation. So that one is x and z of z equal 1/2 z to the minus 1 x2z plus b, let me write this beta, bz. Okay, so I made it on the fly. So the z transform on the fly, which means, you know, I'm looking at the equation, define a difference, and then I compute it. Okay? So you need to get practice. Every time I have a delay, z to the minus 1. And so now, you know, so that means that if I move this one on the left, okay, so I get 1 minus 1/2 z to the minus 1 times z2 is equal to beta z. So that means that, you know, if I continue that, so grouping, collecting x to z, I get that x to z is equal to 1 divided by 1 minus 1/2 z to the minus 1 times bz. Okay. So the system is autoregressive order 1, which is exactly the one that we calculated right now with a row. Remember, the one that we calculate is this. Right here, so you can easily see. So I did this way. I have an input, a filter which is 1, 1, or is it plus or minus? What sign I use? Can I go back? Minus. Perfect. So there is also the corresponding sign. Okay, so at 1 minus rho z to the minus 1, then I have the output. And then I calculate in this case that the autocorrelation R, I don't know, whatever I call it, let's call it x2z, x2n. So R x2, x2, k is equal to the power of the input, which is in this case is beta. And the power of beta is equal to 1. Okay. So that one is equal to 1 multiplied by 1 divided by 1 minus rho squared multiplied by rho to the power of 4. Okay. This one. Which is, you know, is this one. Okay. So I might, in this exercise, I might remember that that one is the autocorrelation order 1, and then you remember these results. But if you don't remember, you know, you can easily derive using what we did in the previous example, previous exercise. Okay. Question. Assume that you know have this nice formula, but rather than giving you this way, I give you, okay, this is a new. I give you 1 divided by 1 plus 1 half z to the minus 1. Assume, okay? So, you know, in this case, this goes on the similar to that one, provided the rho is equal to minus 1 half. So how is the autocorrelation in this case? So, you know, it is equal to 1 divided by 1 minus, you know, 1/4. Okay. Then I have minus 1 half to the power of k. Okay. So that one, the autocorrelation here, it's going this way. If it is negative, okay? This is what you need to copy, not that. Okay. So let's compute the third. Is it clear? I mean, that's easy, I would say. Huh? Now it's getting more complicated because it says, okay, now you know x3. I have a new process, x3, which is equal to x2. x2 minus 1 half x2 n to the minus 1 plus alpha. So now I need to write it, okay? So let me copy that. So I copy now this one. And I solve it separately. Now, let's go. So since x2n is autoregressive order 1, okay, that we calculated by using rho equal 1r, that means that we know, as I said, we know x2, okay, k, which is equal to 1 time, I'm copying, so it is 1/2 to the power of k divided by 1 minus 1/4. This is the result. Now you know, so let me group it. So I can also calculate in this way as a sigma square x2 multiplied by 1/2 to the power of k. Okay? That's the power of x2. Power x2 is when the index k is equal to 0. Now, so what's happened here? Here, x2 is entering to the system. So if I make again, you know, I make the z transform on the fly. So that one is x3z, okay, is equal to, now, it is x2 and the minus 1/2, x2 delayed by 1 sample. So it is 1 minus 1/2, okay, z to the minus 1, x2z plus az. Okay. Now, so x2 is coming, is autoregressive. Okay. So, you know, I can be a little bit smart. I can see that the filtering system is the same as this new system, except here is the 0 and the other is a pole. So if I look at the system, you know, I have beta n, which is filtering by 1 divided by 1 minus 1/2 z to the minus 1. This one was x2n. Okay. This filter, this process is autoregressive order 1. Now this new random process is filtered again by this new filter where I have 1 minus 1/2 z to the minus 1. And then, you know, at the output I sum of n. Okay, so I'm summing up. Now, so question, what kind of random process is x3n? So x3n, you know, is taking the autoregressive order 1 and filtering by 0. So stopping here, the random process is an ARMA because it's an autoregressive order 1 and moving average order 1. So looking at here, you know, it's autoregressive order 1 and moving average order 1, which is an ARMA. Okay. Now, alpha is a white noise. So alpha is introducing noise, but you know, ARMA is the most general one. So that one is ARMA as well. Okay. So, you know, but if I need to calculate the autocorrelation, okay, so look at that. This pole is cancelled with this 0. Okay? So now you have two options. Option number 1 is to start computing as a crazy. Option number 2 is to look at the problem you're solving and say, but you know, what I see here, x3 coincide with beta. And so, you know, here coincide with beta. And then x3 is alpha plus beta. That's it. Because, you know, this filter is equal to the other, the opposite. So the pole is coincident with the 0. If you like, pole and zero cancel each other. So the cascade, you know, they are made in such a way that here I have beta. So x3 is equal to alpha n plus beta n. So the autocorrelation of Rx3 x3 k is equal to the power of alpha plus the power of beta multiplied by delta k. This one is the power of alpha and that one is the power of beta. That's it. Okay? So if you solve it by applying the formula as a disparate, you get this. But you know, it's taking time. Okay, that clear? So you see the difference. Any problem in the written exam can be solved in 1 minute or can be solved in 10 minutes.
Although there is even no process at all when they cancel each other, we call it ARMA, both the output and...
I mean, no, they're random. Okay, but you know, I say if I don't see that they cancel each other, and then I say it's an ARMA because it's autoregressive and moving average. Okay. Clear. So let me write. But canceling the ARMA definition makes no sense. Okay. So you can write. You simply write is a white process. The output. That's it. So the characterization is that the process is white. That's it. Can I look at the last? So you know it's increasing complexity. So the first one can be done by simply applying the definition. Second one, you need to use a Joule worker, okay, or you remember the formula. Third one, you can apply as a starting as a disparate to compute, or you just stay far apart and say, okay, 4 and 0 they cancel each other. So what's the issue? Now let's see the last one. So these are too easy. Now consider y process. So yn is equal to x1 plus x2 minus x3. Okay. So let's write it. X1 plus x2 minus x3. Yn is x1 n plus x2 n minus x3 n. But now, what is x3? Now x3, is alpha plus beta, right? Because, that's by the structure. What was x1? Now x1 was the moving average, order 1. And what is x2? x2 is autoregressive, or order 1. Now, question.
Not the complex. What was
the opposite? Let me read it. X1 was the moving average. X2 was the autoregressive. Okay. And X3 was the one where we cancel each other. Okay. So X1 is moving average, X2 is autoregressive, and X3. Oh, moving average, order 2. Okay. Now, so the goal is, let me see, 1 second. Compute the autocorrelation. Now, how to compute the autocorrelation. Okay, the autocorrelation R, Y, Y, K is equal to, you know now, x1, okay, x1, you know, is autocorrelation x1, x1, okay, okay. Then it's the autocorrelation on the second one, x2, x2, okay. Then what about x3? There's two ways to solve this exercise. So is it minus? Is it minus? Or plus? Minus or plus? Minus. Plus. Okay, you are right. Plus. Okay, because I take any process, I change the sign. Statistical property remains the same. I take any random process, stationary, shift in time. Okay, the one I wrote before, okay? The statistical properties remains the same, okay? So change the sign or shift in time leaves the statistical properties. Okay, so you know, then you sum up and whatever, okay? So that, I mean, this one is autoregressive order 1. Moving average order 2. It's written here. So that one is moving average order 2. That one is autoregressive order 1. So overall, what I expect is that the behavior is a composition of a pole and zero. So very luckily, you know, the autocorrelation for that contains pole and zero, so it's an arma in this case. It's a real arma. The number of poles is 1. The number of zeros is more than 1. Because you know, the R, Y, Y, Z is equal to the sequence, so which is B, Z, B star, 1 over Z, okay? Plus, that one is A, Z, A star, 1 over Z. Plus, that one is 1 plus 1 is 2. Okay? So when I sum it, that one, you know, is A, Z, A star, 1 over Z. Then I have, you know, A, let me write shortly, A star times B star plus 1 plus A star. So overall, I have a pole. Okay. So the order of the autoregressive component is 1. And in the numerator, I have a zeros. So at least I have 2 zeros here. Then I have an additional 1 0, which makes 3 zeros. Okay. So you know what I expect is that there are 3 zeros. So that one is a moving average order 3. So they might simplify, but you know, if they don't simplify, what I expect is the moving average order 3. So overall, it's an ARMA 1, 3. Okay? And we make a break.
Sorry. How did we, what is the intention behind getting rid of cross correlations directly? I guess I missed it. Between